Heat produced within the Earth, mainly from radioactive sources, is transported outwards, first by convection within the mobile interior, then by conduction through the 100 kilometers or so of rigid lithosphere. This process maintains the temperature at the base of the lithosphere at well over 1,000 degrees centigrade. But in some places, hot magma penetrates the conducting layer. Nearly 2/3 of the Earth's heat flow occurs along volcanically active ocean ridge zones. And also on the continents, the sites of greatest heat flow are the volcanically active plate margins. The mechanisms of heat liberation from the Earth's interior are the main factors that have controlled its geological evolution. But our understanding of these mechanisms has to be based on measurements that can be made only near the surface. To illustrate these measurements and the processes they reveal, we'll focus on an important area of geothermal research, the investigation and exploitation of the Earth's heat as an energy reserve. The idea of using geothermal energy isn't new. The Romans used hot water rising from the ground to heat their baths and dwellings. Today, we're no longer limited to natural hot springs, but all geothermal energy production sites have a number of common elements. First, a heat source, which may be just hot rocks at depth, as in a dormant volcano. Second, a heat exchange surface, such as a layer of permeable rocks containing water, known as an aquifer. And third, an overlying layer of impermeable cap rocks to trap the hot water and prevent it migrating upwards. Finally, it must be possible to drill down to the aquifer, liberate the water or steam, and to transport the geothermal heat to the surface. We'll be confining our attention to several contrasting sites in Europe. The heat flow pattern in Europe is closely related to its tectonic history, which in the last 100 million years has seen the closure of a former ocean called Tethys along the Mediterranean line. As the ocean closed, folding, faulting, intrusion and volcanism occurred, forming the Alps, Apennines and also the Tuscan hills of northwest Italy. It is here in Tuscany that the most extensive European geothermal exploration and production program has been carried out. Today, there are no active volcanoes, but there are still signs of hot rock close to the surface.
This bubbling pool is one of the few remaining signs left in an area that was once renowned for its natural geothermal manifestations. But the steam jets and hot water springs have declined in intensity over the last 50 years as more and more steam from underground sources has been tapped for power production. Today, in this region of Tuscany, around Ladarello and Trevale, geothermal steam is being used to produce about 400 megawatts of electricity. And that's about 1.5% of Italy's energy needs. But to understand why this area is so important in terms of geothermal power production, we need to consider its geological evolution.
During the formation of the Alps and Apennines, several major thrust plains developed through the sedimentary cover of both oceanic and continental crust. One important thrust carried a layer of oceanic sedimentary rock about 1 kilometre thick up from the west, fracturing and crumbling the local sedimentary rocks. Tens of kilometres below, ocean lithosphere had been subducted into the mantle. There, partial melting took place and hot melts collected and migrated up into the continental crust. The intrusion of these plutons deformed the surface, causing it to fracture.
This outcrop of the fractured rocks beneath the thrust plain has been brought to the surface by folding and erosion. You can see how broken up it is. It's a brecciated limestone consisting of angular fragments of fine-grained grey limestone and also angular interconnecting cavities. It's through those interconnecting cavities that water can migrate down from the surface to buried layers of this rock, dissolving material and increasing its porosity as it goes. And so it's this rock that takes the water underground where it becomes an aquifer. But most of the geothermal field is covered by rocks like this, fine-grained limestones and muddy limestones. And they're impervious to water. And so they form a cap rock or seal above the aquifer. And beneath the aquifer are rocks like this, fine-grained, crystalline, metamorphic rocks, schists. And they carry heat up from the buried plutons at depth by conduction and also by hydrothermal convection. So we have all the elements needed for a geothermal reservoir: a heat source beneath the basement, an aquifer, and cap rocks to seal the aquifer. But although this area contains all the right elements for a geothermal field, steam only occurs in certain well-defined structures. And so we must use all the available evidence to locate the best places to drill. And that means we must turn to geophysics.
Here, geophysicists are passing electrical current through the ground to measure the variations in resistance of the buried rocks, from which they can build up a picture of the variation of resistance and rock type with depth. The buried aquifer in this region has a much higher resistivity than the adjacent cap rocks. By combining data from remote geophysical techniques with surface geology and borehole data, it's possible to interpret the detailed geological cross-section of the Larderello area. The aquifer outcrops near Monterotondo in the south, where it's intermittently recharged by falling rain. Beneath the Larderello area, heated water percolating to depth within the aquifer either passes back to the surface through near vertical faults, or is trapped at depth beneath the impermeable cap rock seal. Today, steam is obtained from such aquifer traps by drilling to depths between 1/2 and 2 kilometers in the crust.
Well, here they're drilling a new deep test well on the boundary of the main production zone. And they've found steam at about 300 degrees centigrade and 3 kilometers depth. Now, of course, drilling is one of the most expensive parts of geothermal exploration. And despite all the efforts and the amount of time that goes into locating and drilling the best kinds of target, the wells don't always find an economic geothermal reserve.
After the well has been drilled, it will be logged and tested to determine its potential for geothermal power production, bearing in mind that the reserve must keep a power station supplied for 20 to 30 years. Most of the production wells in Larderello deliver steam at over 30 tons an hour, at a temperature over 200 degrees centigrade and about 5 atmospheres pressure. This combination of high temperatures and pressures, known as high enthalpy, makes the steam a sufficiently concentrated energy source to drive turbines and produce electricity.
Geothermal power stations are usually connected to several production wells and also to at least one reinjection well. Reinjection of the condensed steam after the turbine cycle helps replenish the aquifer and also protects the environment from pollution by large amounts of water contaminated with dissolved gases from the well. But volcanically active zones are not the only areas of geothermal interest. Higher than average subsurface temperatures occur in the area around Paris, corresponding with the geological structure known as the Paris Basin. This is a depression in the crystalline basement rocks 500 kilometers wide and up to 3 kilometers deep. It's filled with relatively young sedimentary rocks. Within this sequence, there lie several important aquifers.
Research being coordinated here in Orléans by the French Geology and Mineral Research Bureau, BRGM, has shown that the aquifers of the Paris Basin consist of various kinds of porous sedimentary rocks. The deepest of these aquifers is this Triassic sandstone, which, as you can see, is gritty and it contains numerous little cavities or pore spaces between the grains. The other aquifers in the Paris Basin above this are various kinds of sandstones and limestones, but between the aquifers are layers of clay-rich sedimentary rocks like this red siltstone. Clearly it's not porous and it's impervious to water, so rocks like this form the cap rocks and seals between the aquifers. So the Paris Basin contains two of the essential prerequisites of a geothermal resource, aquifers and cap rocks. But it doesn't contain an obvious heat source. Indeed, unlike Italy, the Paris Basin isn't an obvious geothermal area, and it was discovered partly because of oil exploration and partly because of fundamental research into the Earth's heat flow, which, as you'll find in the main text, is being used to increase our knowledge of the Earth's evolution and thermal history. Now, it's important to understand something about the measurement of heat flow, and so we'll spend a few minutes talking about heat transport through the lithosphere.
Heat flowing from the Earth's interior creates high temperatures at the base of the lithosphere, and the heat is conducted towards the relatively cold exterior. In any part of the lithosphere, such as here, just below the surface, the heat flows down a temperature gradient, which we can express graphically as temperature plotted against depth beneath the surface. The slope now represents the temperature gradient. Let's assume that it represents the temperature gradient for heat flow in average lithosphere. What happens if we replace the top few kilometers by sedimentary rocks with lower than average conductivity? With this temperature gradient, the heat cannot flow through at the same rate, but the build-up of heat in the insulating layer immediately starts to increase its temperature until the temperature gradient across the layer is sufficient to drive the heat through at the same rate as it arrives from below. So compared to average lithosphere, the effect of the insulating layer is to produce higher temperatures near the surface. Remember that in both of these examples we have the same heat flow Q, but the temperature gradients are different. So heat flow is not simply proportional to the temperature gradient, it's also regulated by the conductive properties of the rocks, and the thermal conductivity K is a constant for any particular rock. So in determining heat flow there are two things to measure, temperature gradient and the thermal conductivity. Since conductivity only depends on the rocks, we can conveniently measure it on samples in the laboratory. In this method, constant heat flow is established through an assembly of two insulated metal cylinders with a rock disc sandwiched in between. Under these conditions, the ratio of the thermal conductivities of the rock and metal is simply the inverse of the temperature gradients across them. Using thermocouples to sense the ratio of the temperature gradients in the rock and metal, the thermal conductivity of the rock can be calculated since that of the metal is known.
Having measured thermal conductivity, the other parameter we need to know to obtain heat flow is the thermal gradient. Now we must measure thermal gradient in the field, and it's done by lowering a temperature-sensitive probe like this, containing temperature-sensitive resistances, down a borehole and taking measurements at different intervals. The resulting temperature depth profile is combined with thermal conductivity data to calculate heat flow values. But from a geothermal point of view, where exploration usually takes place in areas which have relatively high heat flow, what we need to know is how deep we'll have to drill in order to be able to find useful temperatures in suitable geological formations. Now, the Paris Basin has been extensively explored by oil companies, and so it's riddled with boreholes. And that means that we know quite a lot about the variation of temperature and geology with depth.
Several of the deeper aquifers in the Paris Basin contain water at temperatures over 60 degrees centigrade. Such modest temperatures make these aquifers low enthalpy reservoirs, and there's no chance of finding high enthalpy steam for the production of electricity. But at Melleray, near Orléans, a use has been found for this low enthalpy energy. These greenhouses are heated by water circulating through radiator pipes. The water used to be heated by oil-fired boilers, but in future these will only run during particularly cold periods. Most of the time, all the heat will be provided by water at 70 degrees centigrade, pumped from the aquifer 1.5 kilometers below Melleray. This will save 1 million gallons of fuel oil a year, and the saving should pay off the cost of the geothermal installation within 10 years. But the water from the aquifer is highly saline and too corrosive to pass through the heating system. Instead, it is passed through a corrosion-resistant heat exchanger to heat up fresh water in the greenhouse heating system.
As at Larderello, the low-temperature saline water here at Melleray is re-injected into the ground to avoid a massive waste disposal problem. But unlike Larderello, the water is also re-injected to conserve heat. Now this is necessary because the economics of low enthalpy geothermal production are very finely balanced.
The lifetime of a paired well system depends on the rate at which heat is extracted from it by pumping out hot water and returning cool water to be reheated within the aquifer. Heat is supplied to the aquifer from below by conduction, but for a practical installation this is too slow to balance the rate at which heat is extracted. Consequently, the re-injected water starts to cool down the aquifer, and a cold front advances towards the production well. Once it reaches it, the system will soon cease to produce water at a useful temperature. So in determining the separation of the wells to give an economic 30-year lifetime, data are needed on the rate and temperature at which water will be extracted and re-injected, together with data about the nature of the aquifer, such as the rate of resupply of conducted heat, the heat stored in the aquifer, its permeability, and the way in which water will circulate through the aquifer.
There are several similar schemes to exploit low enthalpy energy drawn from the Paris Basin aquifers. Here, to the north of Paris, in Creil, water at 56 degrees centigrade is used to provide domestic space heating for 4,000 homes. But apart from the deep sedimentary basins like this and high enthalpy volcanic zones, there are other areas such as southwest England where a different kind of geothermal production, known as the hot dry rock method, may soon become available. Here in the granite moorlands of Cornwall, the first experiments in Europe are being carried out to prove the viability of the hot dry rock method.
Well, we'll take a look at the method in a moment, but first, why is this granite interesting geothermally? Well, you've seen this instrument before. It's a gamma ray spectrometer, and it's been measuring the concentration of radioactive isotopes of potassium, uranium and thorium, the heat-producing elements. Well, that's potassium, high gamma counts. That's uranium, and that's very high for uranium. And that's thorium, also high. In fact, all the granites of southwest England have high concentrations of radioactive heat-producing elements, averaging about 4.5% for potassium, about 12 parts per million for uranium, and 20 parts per million for thorium.
So high heat production is one reason why these granites are of geothermal interest. Another reason is that gravity surveys suggest that the plutons extend to great depth, joining up at about 5 kilometers below the surface to form a huge batholith. So the heat produced in this huge mass of rock boosts that being conducted through the granite from deep within the earth. But although heat flow is high, so too is the thermal conductivity of the granite. Temperature depth data from shallow boreholes in the granite give lower gradients than we would expect to find in poorly conducting sedimentary rocks, but the effective heat production within the granites makes the gradient higher than for average crust. Extrapolating the shallow borehole data to 5 kilometers depth predicts that at this depth in the granites we could find temperatures approaching 200 degrees centigrade. Well, of course, these predictions are only as good as the data on which they're based. In this quarry, scientists from the Camborne School of Mines have begun to test these predictions in boreholes sunk 300 meters into the granite. And if all goes well, then by drilling to 5 kilometers depth, we should be able to find a high enthalpy reservoir.
But there's a snag. This isn't called the hot dry rock project for nothing. These crystalline rocks are impervious, so they're not going to contain any natural aquifers. So this project has two objectives. The first is to verify the projected temperature depth profile, and the second, and more important, is to find a method for developing artificial aquifers or heat exchange surfaces at depth. And if they succeed, it'll be a remarkable technological achievement. But in the attempt, they're aided by some natural properties of the rock, which we can see at the surface in the quarry face.
It's full of joints or fracture surfaces. So this apparently homogeneous crystalline rock will fracture when subject to stress changes. Most of the major fractures follow two prominent vertical directions, roughly at right angles, and the Camborne scientists believe that although diminished in extent, these natural fractures occur at great depth. The eventual aim is to produce deep boreholes deviating at the bottom to give a separation of several hundred meters. Small charges will be exploded in the lower borehole to give good access to the natural fracture system. Then water will be pumped down at high pressure to open up the natural fractures and make connection with the upper borehole, and so produce heat exchange surfaces in the hot granite. At the high temperatures expected 4 to 5 kilometers down, this would produce steam suitable for electricity generation.
The hot dry rock project is simple in concept, but it represents a far more formidable engineering task than anything yet attempted in geothermal energy exploitation. But in principle, the correlations of geological and geothermal features in the three areas we've illustrated are not unique. Elsewhere in Europe, there are other volcanic areas with high heat flow, some like those in Italy and others in continental rift zones. There are other sedimentary basins with low conductivity layers and buried aquifers, and other crystalline granitic masses, many with high heat production. Clearly, there's potential for future expansion of geothermal exploration, and with this, we'll continue to improve our understanding of the patterns of heat flow, heat production, and subsurface thermal gradients in the continental lithosphere.